kind of economy. So
economics?
yeah, economics.
Oh boy, I'm interested in that too. But remember, this is engineering.
Yeah. So
but we can talk.
Yeah, what is the relationship? Because I saw there is the job opportunities about JP Morgan's. So how it's related between.
So most of our students certainly take jobs at traditional engineering companies.
Yeah.
You know, the Honeywells, the Intels, et cetera, and so forth. NASA, and I could go on and on. But there is a small subset, you know, I might say that it might be every year, it might be 2 to 5% that are interested in, I want to go to Wall Street, make some money. And so our students have been very successful in getting those jobs as well. I've sent a bunch of students to Wall Street. And they're using ideas from controls. Because controls fundamentally is decision making in the presence of uncertainty, and buying stocks, bonds, trading is making decision in the presence of uncertainty. Here in controls we use mathematical models. The mathematical models here tend to be based on physics, the chemistry, the biology, whatever science applies. And most of these have been very well grounded. The physics, certainly for hundreds of years. We understand a lot of the physics. We understand a lot of the chemistry. We understand a lot of the biology, but biology, relatively speaking, is still in its infancy, in that we have just begun to quantify things. It's been very qualitative. We know this. We all have gone to a doctor, and the doctor says, take 2 of these. And it can't be you take 2 of these for everybody. But that's what they do. And that's changing because of this thing called genetics and sequencing your genome. Thank you. I knew I had the word gene in there, but I was missing something. I think I still need some oxygen in me. So I haven't priced it recently. I follow these things because I'm interested. But sequencing your genome these days is far less expensive than it was even 5 years ago. It might be like a couple $100. And what I'm getting at is that will become standard. Eventually will become standard, and then doctors will treat us as individuals. That's an area called personalized medicine. That's happening. We are living in revolutionary times, and this is not me, no one has paid me to say that. This is a fact, and I'm just, this is an inarguable fact. I've had the opportunity to work on robots in the air, robots on the ground, high-performance aircraft, missiles that go after those aircraft, space systems, space robots, space weapon systems to shoot down those missiles. And so I think a lot of cool stuff. But the stuff that you folks will have, that have available to you, is just incredible. And I'm not just talking about the driverless vehicles, which, I mean, I've been working on driverless vehicles since the early 1990s. Oh boy, I feel old saying that. But yeah, we tested driverless vehicles in parking lot, 59? That still is the end of the world here, right? Is it? Is it still fairly the end of the world for students? Yeah, parking lot 59, we had a couple of vehicles there, and they were following each other driverlessly. And a few times we had permits, and other times, well, we're on camera. Other times, we just went with it. Now, I was a young assistant professor there so they would just blame everything on me, I guess. So. The older professors, I don't know. It was fun. It was fun. I expected driverless vehicles to be around much sooner. I did not take into account one thing, this thing called the lawyer and legal aspects. I think no one was able to take that into account. Even today, and there's been tremendous progress, as you see, even today, there's still a large community discussing this subject. If you look carefully, you see it's being discussed. What's going to happen when this happens? You know, okay, then thousands of lawyers will come out and shake things up. So I'm bringing these things up because there are a lot of cool things that you can work on. And I think that's really important. And controls will allow you to work in any of these cool areas. Certainly if you want to work, another area that is that's still in its infancy, quadcopters. It's in its infancy. You could think of it like it got started last week, almost. And I've had a lot of my students graduate, take on jobs at quadcopter companies, doing all sorts of things, image processing to recognize people, recognize, okay, that's a tree, you know, some standard AI stuff, but obstacle avoidance, that's kind of important to do autonomous navigation. Okay, so let me ask you again, are there any other questions you might have? And then I want to really get into the presentation with some details. Okay, here we go. So I really like controls, still after many years. This is my 30th year here at ASU. It feels like 7, but when I go look at myself in the mirror disagrees with me. Okay. The mirror looks at me and goes, 7? Are you kidding me? Okay. So I've been using this presentation for quite a while. We are living in revolutionary times, but that has become truer and truer every semester I use this presentation. You know, like I said, I could. I think where the most outrageous stuff is being done. Now, I've already told you, I've worked on all sorts of cool things, and I'm not saying that to brag. I'm saying that to give you some perspective, so that if you start thinking about what opportunities are in front of you, you can start planning your work, working your plan, and you can work on many more cool things than I ever did. Okay, so I've worked on vehicles on the ground, vehicles in the air, all sorts of vehicles, economic systems as well. But the things that are available today are just incredible. But the most incredible thing is happening in the medical arena. We are able, using stem cell research, we are able to figure out what tendencies you have towards certain diseases. That's amazing. But more than that, we're able to clone. I mean, imagine cloning, right? All right, now there's some problems with it. There are some problems. Usually there are technical problems that need to be figured out. But, you know, cloning, I mean, when's the time when they cloned the sheep? And they've cloned a bunch of stuff now, but, you know, it might be like 10 years ago, something like that. But using stem cell technology, we can repair organs. Okay, I just went from cloning to repairing organs. Cloning is sort of, okay, that's still future stuff, you know. We don't want to really make that mainstream. It's not ready to be mainstream yet. But repairing organs, they've been repairing all sorts of organs now for a long time. And repairing them really well. Not only have they been repairing organs, they've been growing organs from scratch in the lab and putting them inside people, and they work really well. So again, I'm electrical engineering. All my degrees are in electrical engineering. However, I read about these things because controls applies everywhere. And that ultimately, that's why I fell in love with controls and decided to do controls. I liked all the other areas within electrical engineering, but I chose controls because I could see, I could apply it to antennas and electromagnetism. I can apply it to circuits. I can apply it to communication systems. I can apply it to signal processing, etc. and so forth. And certainly chemical systems, biological systems, robotic systems, space systems, etc. and so forth. So yeah, the medical arena, that's the coolest, because we can grow organs, and that's essentially, recreating life. So that's cool on another level. I think objectively speaking, that's cool on another level. I've had some of these discussions, philosophical discussions, with some of my colleagues that are physics lovers like me. And I said, okay, when the physicists learn how to create a planet from scratch, not blow one up, but create one from scratch, then okay, then they're on the same level creating life. We're not there yet, but it's coming. It's coming. And again, I'm saying these things because it's a matter of you picking what you want to work on. I've got students that are working on brain-powered prosthetics. And that is mainstream now. I mean, that's being used, and that's been used now for quite a while. And that's pretty amazing stuff. I've had students work on exoskeletons. The idea is that you put on this electromechanical exoskeleton, sort of like suit. Makes you look a little weird, but it can make you a lot stronger. You have one. I have 3. God. So I'm just joking. I don't have one. But it would be cool. One day you'll have this conversation. And now, you don't really have one, do you?
I don't think so.
I don't think so. I thought you were joking around. But there are students that are working on them. And so you will encounter students here that say, yeah, I've got 3 of them in my lab, working with Professor Tom Sugar in mechanical engineering. So, I mean, why work on exoskeletons? They can help soldiers, certainly, okay, but they can also help the elderly. And just in case you might not think it, you too will be elderly someday. Even though some of these technologies will maybe help you handle the elderliness in a more graceful fashion, that is so true. But you should think about these things. All right, let's keep going. And if you think of any questions at all, you can ask anytime you want. So I'll talk about what is controls, where is controls used, the courses, the faculty. I'll mention the faculty right at the very beginning almost. Job opportunities, we've already started talking about that. Today there's robotics has exploded. Artificial intelligence. I can't turn on the radio without hearing artificial intelligence. Well, that shows you maybe the radio stations I'm listening to, maybe. But the advertisers, typically a big company, and a lot of the big companies we're doing AI in order to deliver better services and products, etc., and so forth. This is not going away. It's here to stay. There's always been fads. There's been AI fads in the past. And this is still a wave, but it's a huge wave. And it can employ all of you very easily. And the reason I bring that up is because controls is fundamentally about making something behave in a reliable, predictable manner. And certainly I can point to the thermostat control in a building, right, controlling the temperature. Here in Arizona, we might be a little bit more sensitive to that. Oh yes, that's a very important problem. They might not, or if you're in Minnesota, they might think it's very important there as well. There's also speed control in a car, which probably most people just take for granted and don't even think about it. I remember the first time I explained what it is that I do to my uncle. And this was some 30 years ago when he was picking me up at the airport. He lived here in Arizona. And so I was explaining what controls was, and I explained the cruise control for a car. And he was very direct, and he pretty much said to me, you know, I should take you back to the airport and send you back, because why did you spend all those years just learning cruise control for a car? But then before he took me back, I said, well, hey, it also applies to airplanes. And now he worked for airlines, so then he began to understand. He said, oh, okay, that's useful. And, you know, and missiles, right, and missiles. And he says, oh, yeah, then maybe you should stay here. But you get what I'm trying to convey is the following. A lot of people, they have interacted with control systems in lots of places, but they don't really know what controls is. But those examples, controlling the temperature in this room, I was going to say furnace or semiconductor furnace. I think that applies too. We're in Arizona. Controlling the temperature in a semiconductor furnace, that's a challenging problem. It needs to be controlled very precisely, because otherwise you got to throw out all those 1,000 wafers, each costing, you know, a lot of money. And someone's going to get fired when that happens. That's not a pretty thing to see. So controls is about whenever something needs to be done precisely. How do we do things? When we need to do something precisely, typically what we do, we use our eyes, we use our brain, and that system is a feedback system. That's a feedback system. And we use our eyes, our ears, nose, etc., all our senses in order to figure out, in our brain, in order to figure out what to do and try to get better at it. And by repeating, we get better and better in principle, right? So that's that. If you think about that, then you see how it can be used to control a nuclear reactor, control a high-performance fighter, control, here's a tough one, control an economic system. Here's an even tougher one, control a viral epidemic. I won't say anything more about that. All right. No, actually, if you have questions on that, we can discuss that as well. But that's a controls problem. Okay, it is a controls problem, and I have friends that are working on that. And I mean really working with the CDC on developing policies to do things right. But whenever people are involved, that makes it much more challenging. It's not like controlling an airplane. When you control an airplane or a car or a robot, you're dealing with electromechanical systems, robotic-like systems, hardware, and you attach a computer to it and sensors, and it will. You can control it really well. You can't easily attach a computer to people to get them to do their laundry late at night. You know, when the electricity load on the grid is lowest, say. You get what I mean? Okay. You got to give them incentives. And even then, they might not pay attention to the incentives. Okay, let's keep it going. What is controls? Already I've started telling you a little bit about it. I really told you the most important thing, but let's nerdify it a little bit to make it a little bit precise. So I use this feedback diagram to convey what control's about. This Y here represents the actual system output. You can think of it as the temperature of a semiconductor oven. You can think of it as the speed of, how about an aircraft, a spacecraft, not an aircraft, spacecraft. Or it could be anything else that you want. It could be anything. So when I mention controls, all that is required really is this. There is some variable you wish to control, and then there's some sort of an input that you adjust in order to control that variable. Okay? So I mean, going to the coronavirus thing, we want to control the number of cases. We want to minimize the number of cases. And so then we try to provide appropriate incentives and resources to people so that they do the right thing. So that they do the right thing. But now this is a very sensitive matter because it involves people, and they could be scared, and so that's another subject. People work on that, modeling fear. Decision makers work on that, modeling fear, because that's part, when you're dealing with people, you have to deal with fear. And modeling the politics, and modeling all these things. Okay, so we have this system P called the plant that we wish to control. That represents the airplane, the robot, whatever, the economic system, whatever system that you're thinking of controlling that has inputs and outputs. Like I said, Y here represents the actual output. The idea is that we're feeding back that actual output through a sensor. Whenever you feed back any measurement, there is always going to be sensor noise, always. Always. And then you compare it to a desired output. You feed back the actual output, you compare it to the desired output. So think of the desired output as your desired speed, for example. And I use that example only because I think that's easy for us to process. We see cars all the time, and airplanes. And so an error signal is generated, and this controller, this is what you will learn how to design in our control classes, and we design the controller on the basis of a mathematical model for the plant and some knowledge of the noise that you have, what type of commands you want to follow. Okay, so maybe I want to follow this command. That was just meant to illustrate an idea. I mean, do you want to follow step commands? Do you want to follow sinusoidal commands? What do you want? How fast should the commands? Do I want to go from 0 to 60 in so much time? But I can go on and on. You get what I mean? If it's an aircraft, or how about a drone, pilotless drone? It may have to do that in order to catch what it's going after. And so, how fast can it do that? Okay, and so the idea is that we have a control system designed so that it follows whatever commands are given to it. Okay, and those commands could be given by someone who's watching a video and then issuing commands via a joystick. Or they can be generated automatically. Okay, on a missile, a lot of missiles, many missiles are fire and forget, and so there is a guidance system on the missile as well. So there is another feedback loop, and there's a block over here called guidance system, and the guidance system figures out what command to give to the control system. And so that guidance system is figuring out, do we accelerate to the left? Do we accelerate to the right? Accelerate upwards, accelerate downwards, etc. So that's just another level of controls. Okay? And so this is like low-level controls, and that guidance system is like the higher level of controls. And that guidance system is closer to what you see and hear about in the artificial intelligence community. Okay? But like I said earlier, this control stuff will give you a background to go into any one of those classes and handle them really well. You will bring a foundation. I was just talking to several students of mine that are taking a class with other some non-engineering students, and they don't typically have a systems background, and if you don't have a systems background, then it doesn't matter how well you program in Python and C and Java. Those things don't matter. Because ultimately, when you're doing the fancy stuff, it's not the Python, the Java, and the C programming that is really the critical issue. The critical issue is all of this stuff. And yeah, math. Controls, I'll tell you right at the beginning, controls tends to be more mathematical than some other disciplines, but they're all mathematical. It bothers me a bit sometimes when they say that controls is more mathematical, and they're talking about electromagnetism. Are you kidding me? There you have Maxwell's equations. People look at Maxwell's equations and pass out, and there's just a few of them. You got 4 equations, you look at, I don't want to do this. Controls may not have just 4 basic equations, it's got a lot of smaller equations, a lot of concepts. But the fact of the matter is, in any area, if you want to do sophisticated work, is going to be mathematical. Now, having said that, in any area, there's a spectrum of things. I mean, you can go from building hardware, writing software, developing the algorithms, the mathematical models. That's, pretty sophisticated stuff, because ultimately that dictates how the stuff works. Okay, and then there's sales. So there's room for everyone in any of these areas. Okay, we want to design this controller on the basis of a mathematical model for this plant and knowledge of noise. These here, DI and DO, represent disturbances at the plant input and at the plant output. You need to have some knowledge of what the disturbances are going to be, otherwise you'll be in trouble. Imagine an airplane coming in for a landing. When you're coming in for a landing, what's the first thing that you see, besides the ground and houses and whatever? At the airport, what do you see? Do you see these little things that are spinning? Like they're anemometers, they're wind speed devices. Do you know what they're there for? They're there to try to detect wind shear. Wind shear, in short, really refers to abrupt changes in wind direction and speed. That's kind of important, especially if you're the one that's coming down for that landing. And so if the pilots get a message saying, hey, we got wind shear, they abort the landing. Usually when they're landing, they're very low on the throttle, low power. Why? In case of an emergency situation, they can then go to max power and climb out of there. Okay, so there's wind shear detectors. There's always disturbances. That's my point. Always, in any problem. And so you learn how to design K on the basis of the models for these things in these basic control classes, and we want to design the control system such that this control system delivers predictable, reliable performance. That's why we need the math. That's why we need the math. Remember, we're engineers. We're not hobbyists. Most hobbyists just try to do something cool. They, use some of these feedback ideas, and I've known some 11-year-old hobbyists that are phenomenal. Really phenomenal. And some of them, actually a bunch of them I've seen, have been great engineers at age 11, 12, because they've learned some real engineering stuff, even at that age. I always tell the story of a 12-year-old knocking on my door at like 7 o'clock in the morning, 20 years ago. And he said, and he's with all his stuff, and he says, my daddy says, you're a professor at ASU, and I want to talk to you about my robots, and I want you to tell me what a PID controller is. At 7 o'clock in the morning. I had gone to sleep probably at 6 in the morning, so I was a bit tired. That kid went on, he went on to get an engineering degree and has been working at Ford on driverless vehicles for many, many years. And I watched him race competitively. And that little guy was using a lot of concepts that I teach in my classes. Except I teach it with a bunch of equations, and he was just, basic understanding. And that basic understanding should come first. Okay? Hobbyists usually are not seeking reliable, and the key word is predictable performance. Meaning that if I say I want the error to be I want to follow this trajectory to within 2 inches, then that's what I mean. You know, not plus or minus 1 foot. Because then we become hobbyists and then we become unemployed hobbyists. So that's not cool, all right? So that's why we need all this mathematical stuff, all right? And the example that I typically give is the cruise control for a car, but it can apply to the altitude control system for a spacecraft landing on a planet, speed of an aircraft, speed of a missile, etc. All different types of systems. This is hypersonic vehicles. Hypersonic vehicles are vehicles that go 5 times the speed of sound or faster. I've had the privilege of working on hypersonic vehicles. Oh gosh, it's been 16 years now. Yeah, I didn't think about that until just now. 16 years. If you watch some of the political stuff, every once in a while you will actually hear something substantive. You know, look in, maybe once a week or something like that, and you might hear something substantive. And just about 2 years ago, the Soviet Union they announced that they were deploying hypersonic vehicles. And so that's just something to just let you know about. Okay, it's a fairly new thing. Okay. There's a lot of, this is the nerdy slide. We will not go over it. There's disturbances, nonlinearities. In these classes that you will take, most of what you will use is linear differential equations. Now you'll learn how to take the nonlinear differential equation, linearize it, and it becomes a linear differential equation. But 98% of the effort is going to be linear differential equations. And I make a big deal about that. Why? You are engineers, you are systems people, and if you go and take AI classes, machine learning classes, and you bring this system perspective, you will be ahead of everybody else. In a big way, not a minor way, in a huge way. Now, they may know how to program really, really well. That's something, hey, there's genius programmers. Most of who you'll be dealing with, I assure you, is not a genius programmer. They could be good programmers. You can pick that up. Picking this stuff up, I don't think you can pick that up. That's not easy to pick up. You really, really need a class for this stuff. And classes. This is more nerdy stuff. I already talked about some of it. Where is controls used? It's really used everywhere. It's inherently multidisciplinary. So I told you I've been working on hypersonic vehicles. Now, am I an aerospace engineer? No. However, if you talk to me for about 15 minutes, I can convince most people that I am an aerospace engineer. Because of my background, I've just learned a lot about that stuff because I like it. Okay, and that, whatever I am working on, I just dive in and try to learn as much as possible. Okay, and like I said, controls applies to all different areas. So when I was working on some nuclear reactor stuff, I learned about nuclear reactors. Economic stuff, which I love, because I've got young kids and I got to send them to college. Okay, you know how much a book is going to cost they're 14 years old. How much a book is going to cost in 4 years? I've seen the numbers. It doesn't look good. It's going like, how much is a book these days? $200 and something? Huh?
That's 500 sometimes.
You've seen 500?
Yeah.
But I'm talking to someone who has an exoskeleton. That's really expensive. So you got the bucks. All right. All right, let me keep going. Where is controls used? This list, and you have a copy of this, right? It's crazy, and it just goes on and on. You want to design a new. Here you go. You want to design a new Gamage auditorium. There you go. Feedback, echoes, echo cancellation, all that stuff. That's fundamentally a controls problem. Okay? So I've gone into some rooms where you go in and you drop almost anything and you hear it reverberate around the room. And you go like, wow! It's like the room is going to fall apart. And then they will turn on, bless you, they will turn on sensors and sound generators. And then you drop the thing and you hear almost nothing. And it's like magic. When you see controls being used, it always looks like magic to most people. And by most people, I mean 99%. And that includes the professors too. I've shown controls to professors and they get that little kid look like, wow, how'd you do that? It's math. You know, the stuff that you torture students with? Then they, oh, now I understand. All right, okay. So all these areas, I mean, it just goes on and on. Capital investment, there's the economics. So sent students to doing portfolio management on Wall Street, buying and selling securities. Okay, which all of you should learn about because all of you one day you will graduate and you'll be paid really well. You'll have a lot of money and you'll have to learn how to invest. And so you really should all learn about economics and investment. I felt obligated to say that. Let's keep going here. So medical I talked about, and there's other areas. Space exploration has always been, I've done a lot of work with NASA, and that first spacecraft that I showed you is called JIMO. JIMO stands for Jupiter Icy Moon Orbiter. JIMO was designed at the Jet Propulsion Laboratory. It has very large solar appendages. All aircraft have large solar appendages to get energy from the sun and power everything on board. You know, and there's nuclear reactors usually on board as well. JIMO was designed to explore the moons of Jupiter, a Jupiter Icy Moon Orbiter, and specifically the moon Europa. Now, JIMO, they made the solar appendages too big. And I was on the controls team, and we're the ones that told them that it was too big. They wanted to perform certain maneuvers. You got to maneuver the spacecraft and point the science platform certain amount of degrees of accuracy, and move so fast, etc., and so forth. And with that huge solar thing, we could not control it reliably. You had to either give up on the speed, it was too fast, or you make it smaller. And they did not appreciate us telling them that. They even said some things over the phone that I knew were inappropriate. I heard it, couldn't hear it very well, but it was inappropriate. The next day they called us and said, we'll redesign, over the next 2 weeks. JIMO is going to be used by the European Union over the next, and I haven't followed this, but over the next couple of years. Mission to Europa. One of the holy grails of science is to detect life on a planet. Now, when I say life, I'm not talking about, a professor, waving a flag over there. No, any type of microbe, living microbe. It would be revolutionary. And so Europa has been targeted because its polar caps have ice, oceans, water, etc., and so forth, and they suspect that there could be life there. So that's why we're going there. Yeah?
This mission is projected for 2038, right?
No, that's far away. 2038, that's far. It's sooner.
Oh, sooner?
Yeah, oh yeah. So I just said within the next couple of years. I mean, the last time I looked at it, which was probably a couple years ago, it was projected for the next couple of years.
I was, because I remember hearing about this Europa expedition, but like...
There are many robotic expeditions, probably even to Jupiter. There's not just one, I'm sure. There's many going on that people are working on in different time frames. A lot of cool stuff. It's a matter of picking. Don't get stressed out by picking, though. That's a good thing that you have many options. Don't think about trying to find the perfect anything for that matter. Okay, I think we all get into trouble looking for perfection. There's nothing perfect, except my wife. That's it. Am I right? That's it, right? That's it. And I'm on camera. I got it on camera. Okay.
Don't worry, we'll send her today's footage so she knows.
She knows. Please. Okay. And I'll pay for that that service. So this is serious. Don't look for the perfect job. That's hard, impossible to find. What you should look for is challenging, cool opportunities, and you're going to have many of them over your career. And you will be jumping from one to the next, to the next, to the next. It may be within the same job, within the same company, but it could be changing jobs within companies. And then maybe after 15 years, you might go to another company and take your knowledge somewhere else. Okay? All right. Let's keep it going here. It's a pretty amazing list. That's why I fell in love with controls. In terms of courses, well, it begins with, there's circuits. For me, my first and second circuit classes, they gave me the foundation. Yes, it's circuit analysis, but there's some Laplace transforms there, Fourier analysis, transfer functions, Fourier series, maybe signal systems, concepts. It's the foundation. And then came signals and systems. So I just want to tell you, I took the same type of classes. Okay. Something that comes up is, should I take signals and systems at the same time with 480? Well, you can see what the prerequisites are and what co-requisites, and I don't define those here. All right, not at all. So you could check with your advisors, and please go to your advisors. You have great advisors that you should take advantage of. They do an excellent job. Okay, and you can always, come see me anytime. After we're done here, I could give you my phone number, and you can call me anytime. Just a few days ago, I spoke to at least, it was exactly 4 students about this, pathways and controls, and we talked for a while. And we probably spent more time than I'm going to spend here with you. The 2 basic control classes that we have are 480 and 481. I typically teach 480, okay? However, Dr. Sakalis has taught 480 in the past, okay? 481 is the other controls class. I've taught 481 in the past, so has Dr. Sakalis. But more recently, one of Dr. Sakalis's former PhD students has been teaching 481. And so let me say something about these 2 classes. 480 is mainly continuous time, analog, Laplace transforms. 481 is intended to be the simpler, simpler, more applied class. And so in that class, you learn a little bit about how to design control systems, but then you also learn how to implement them in a digital system. Okay, and that could be like a microprocessor, okay, or a microcontroller, or it could be an FPGA, field programmable gate array. They might talk about it, but they focus mainly on microprocessors, and they talk about microcontrollers in that class. All right, now 481, as I said, is supposed to be the simpler and more applied class. However, based on what I just discussed, it contains continuous stuff and discrete stuff. So that means Laplace transforms and Z transforms. So in that sense, there's more concepts. Okay, so that's just something to be aware of. If you're only going to take one controls class, and that's it, and you don't plan on doing maybe more advanced work in controls, then I would say take 481, because then you get exposed to everything in one place. All right. If you do intend to do advanced work in controls, and later on do AI stuff, artificial intelligence, etc., maybe machine learning, robotics, whatever, any of that stuff, then I would strongly suggest that you take 480 first and then take 481. If you take 480 first and then go into 481, you'll have one hell of a background, and you will be at a tremendous advantage to students coming into 481 that are seeing controls for the first time. I mean, they don't know how to compute a transfer function for a feedback system, whereas you not only know how to do that from 480, but you've been designing control systems for an entire semester. So certainly if you want to do more advanced work, I would say take 480 and then 481. Traditionally, that's the way it's been done across the nation and around the world for decades. However, because of demand and what students want, etc., and so forth, they want to start doing things right away. So we thought, okay, let's offer a more applied class that they could take. But everything has a cost. Everything does, and we learn about that in economics. The economics guy left. Okay. At the graduate level, we've got linear systems. I've typically taught linear systems in the past. Dr. Sakalis also teaches linear systems. He's been teaching it recently. There is nonlinear systems. That's 586. If I had to pick the hardest class that we offer, it would be nonlinear systems. That's the hardest class that we offer out of all the classes that we offer. Okay, I think that my colleagues might agree with that. So far I've mentioned myself as a controls professor, Dr. Sakalis, but pretty soon I'll get to Dr. Jenny C. Transform theory, that's a class that both Dr. Sakalis and I have taught in the past, but usually it's someone from the signals area that teaches that class. There's random signal theory. There is robust multivariable control. That's a class that I have exclusively taught for the last 30 years. Whew. Sounds like it's crazy. There's optimal control. Optimal control has been taught by Dr. Sakalis. Dr. Jenny C. is teaching it this semester. So I assume she will be teaching it in semesters to follow. I haven't taught that class. I would love to teach it, but I've got other things to do, to teach. And okay, neural networks. That's Dr. Jenny C.'s baby. Neural networks. She does a lot of research on neural networks, machine learning, deep learning, brain science. Dr. Sakalis also works on, has worked on things related to the brain, the detection and suppression of epileptic seizures. Epileptic seizures. So there's a tremendous amount of opportunities. Both of these professors, Sakalis and C, have worked with animals in the lab, rats, monkeys, etc. The idea is that if you can understand how they work, then you can help human beings. And this is a sensitive matter because there's animals involved. So I'm on camera. Don't get angry with me. No, it's a sensitive matter. It's a sensitive matter, but these are serious researchers following the rules of the nation, and they're cool opportunities for you. It's just a matter of you grabbing it, and I certainly would think about it if I were you. We know a lot of things about the human body. There's the brain. That's something where we really, there's a lot that we don't know about. So over the next 20 years, we're going to learn so much about the brain. And so I recommend strongly to young people that are interested in biological applications to dive into brain science, because that is going to see things that are just extraordinary. And I've already seen extraordinary things being done in the brain science arena within a military context, because they're going to jump on that first, usually. Okay, there's filtering of stochastic processes. Dr. Jenny C. has taught that class in the past. Adaptive control, that is Dr. Sakalis's baby. He's been our adaptive control person, period, and he's teaching it this semester. Okay, and I would recommend that before you take adaptive control, you take linear systems and nonlinear systems. But before going into any class, you go speak to your advisors and go. Is it the blue sheet? Is it still blue? The blue guide. The blue guide. It used to be a sheet. You see, now it's a guide, many pages. It's a long time ago that it was a sheet, many years ago. You might want to go speak to some of the professors that you're going to be taking classes. I always try to counsel students, if you're not sure, go speak to the professor so you can see what you're getting yourself into, what they really require and what they don't require, what their expectations are. I know this might make you feel uncomfortable, but hey, that's part of the learning process. Being uncomfortable. Later on, when you graduate and you get paid all that money, they're going to be paying you to feel uncomfortable all the time. And I'm not saying that really in a negative way. That's just part of it. You have to learn new things, and learning new things is always going to be a little scary and uncomfortable. But if you bring the right attitude to it, that that's cool, I want to attack it, then I think you'll be better off. If you're, I got to learn something else, that's not good. Not good. Okay. Other courses that our students have taken over the years, and I mean 99% of our master's students, myself, Dr. Sakalis, Dr. Jenny C., 99% of our students or so have taken system identification, which has been taught traditionally in chemical engineering by Professor Dan Rivera. Okay, it's being offered this semester, for example. A lot of these more advanced classes, typically the more advanced classes are offered at the graduate level, they're offered every 3 semesters. That's something to be aware of, to plan. Okay? Another class that our students have typically taken is applied optimization, and that has been taught in the math department by Professor Middleman, Hans Middleman. And almost all of my graduate students and Dr. Sakalis and Dr. Jenny C. have taken Middleman's optimization class. There are some other optimization classes that are being offered now these days that I've sent my students to. They're really good optimization. And just think about optimization a little bit. We're trying to design a system to work well. So the idea is, we want to improve performance. The idea is that we want to optimize performance. How good can we make the performance? And typically, if you're trying to improve something else should get worse. Unless it's a little kiddie example in a textbook. Only in a little kiddie example in a textbook you can have your cake and eat it too. You get what I'm trying to say? In real world, which is not kiddie, you try to improve something, it comes at a price. You know, there's no free lunch, as they say in economics. Okay, and then there's no free lunch in anything. Okay, right? Someone paid for the pizza. And it may have been you indirectly, right? Indirectly. Okay. Some of you did not laugh at that. That wasn't funny. Yeah, I understand. Remember, I got kids. Textbook is going to cost a fortune. Numerical analysis. That's another class that our students have taken over the years. The more you know about numerical analysis and using computers to solve mathematical problems, the more you can participate in this crazy technical revolution that the world is experiencing. Artificial intelligence, robotics, drones, driverless vehicles, personalized medicine. You can just go on and on and on. And there's revolution taking place in material science. There's revolutions taking, it really is incredible. Okay, did you have a question? No? No. Oh, he's just scratching his ear. Look, he has his hand like this. It looks like he's about to launch. All right, okay. At the master's level, there are several options that you have. I usually recommend, most students take the MSE exam. They take the exam. You take a bunch of classes and then you take an exam. You got to solve so many problems. You got to get a 70% or above to pass, something like that. And that's what most students do. Another option that you have is to do the thesis. I recommend that if you are really interested in something and you want to show those employers that you know, we got a minute left, that's what that means. Uh-oh, I'm in trouble. Okay. Okay, and if you want to really show those employers that you've really learned something, then I would beg you to do a thesis. But it's up to you. Why don't students do a thesis? Now, do they like exams? What's the answer to that? The answer is hell no, not no, it's hell no. But they prefer the certainty of an exam at the end than a thesis. Oh, and you got to work with a professor. Okay, and there's uncertainty there. But certainly, hey, you're going to go out there, you're going to get a job, you're going to be working with people. And if you do a thesis now and you can put that on your resume, then when you get out there, you'll get the cooler job faster, or you get hired faster, you get the cooler job faster, you'll be given more responsibility faster. And, and I've seen that with a lot of students. My wife, she didn't do a thesis, and I think if she had done a thesis, then she would have gotten into those cooler jobs faster. And I could have a lot of student examples to speak of. There's another thing I should talk about. There's the 4+1. 4+1. That is a good deal. Now, ASU is not telling me to say this. It is a really, really good deal. Please take advantage of it. You got to have was it a 3.5 GPA? To get accepted into it. So do your best to try to do that. Getting your master's in one more year is very cool. I want you to get your master's not because you're going to be making $10,000, $15,000 a year more, although that's kind of cool, but because by getting your master's, you'll see. Speak to some students that are getting their master's and that are applying for jobs. You will hear them say, and I quote, "They treat me different. They didn't see me before. Now they actually see me." And I'm just quoting what many students have said and what I've heard for many, many, many years. The main reason is not just so you can get that job, it will help you get the job. Getting that master's will help you get the much cooler job. And I think that's important. If you get a job that you really like, then there's something to it that if you really love what you're doing, then okay, it's not work. It still is work. But there is something to it. Okay, I'm not faking this smile. Okay, that was a little fake, but it's really just a little bit. I love my job. Okay. And now you should love yours too. So yeah, get your master's. And I told you, I spoke about most of the controls faculty, Sakalas, C, Rodriguez. There's also a Professor Lai. He works more on brain science type stuff. He doesn't teach any of the controls classes, but he's a world-class researcher. One of my students works with him right now. We work together. Really cool stuff. Again, brain science stuff. So there's lots of opportunities, lots of topics you can work on with any of these professors, lots of applications, many application areas. Job opportunities, you got a list. There's a lot of companies. Where'd I go? I don't know where I'm, let me see. Okay, yeah. There's a lot of companies. Now, they might have a job that doesn't say the word controls. But it says using machine learning for robots. Well, I don't care what it says. If it says machine learning for robots, a controls background will help you tremendously. Let me say it a different way. If I'm hiring someone who's going to use machine learning on robots, then I want someone, so if it's a serious machine learning algorithm that involves using sensors and feedback, I will certainly want a controls person for that type of, I want someone with controls background for that type of application. Make sense? Someone who understands feedback and feedback systems. Because remember, in any application, robotics, driverless vehicles, we're trying to do something precisely, which means that we're trying to make some error small. We want the vehicle to follow a path to win a very small error. We want the robot to pick up something and bring it to something within a certain error, etc. and so forth. And so feedback is really, really important. Yeah, programming, that's of secondary importance. It's important though. You know, I advise all the students to learn how to program. And I make a big deal about it because a lot of students don't like programming. That's not good in this day and age. In this day and age, I think 98% of the engineers are going to be programming something. And this is across all disciplines. It may not be 98%, it might be 94%. But it's 90-something percent. It's up there. It's up there. Okay, I think I'm, for the most part, done. Maybe you can ask me a couple of questions if it's okay. You can ask me anything you want, anything at all, anything at all. I think they don't want to do controls anymore. No questions? Yes, a question.
Other than programming, what do you think are the most important skills to develop?
In programming?
Other than programming, what do you think are the most important other skills to have going into?
Other than programming, so I'll begin, you should learn how to program in C. If I had to choose a language for you, it would be C++. Within programming, learn about objects, object-oriented programming, structured programming. That's really important. Now, getting away from programming, then it becomes very specific. If you're interested in robotics work on the ground or in the air, then I might suggest that you maybe learn a little image processing, because robots on the ground, robots in the air typically have a camera, and processing those images is becoming easier. You've heard of a company called NVIDIA. They make GPUs, graphical processing units. That's one stock that I have not bought, and it's sad because I've been watching them for many years. I expect there to be a GPU revolution taking place. Now it is taking place, but it's taking place within the gaming community. Any gamers here? No gamers. I'm not a gamer myself, but I know serious gamers, really serious gamers. And so learning about GPUs, so these GPUs allow you to process, for example, images in parallel, the data in parallel. And by processing it in parallel, you can process it much more rapidly. And then you can use a facial recognition algorithm. What's your name?
Adam.
Ah, that's what my facial recognition algorithm told me. Adam?
Adam.
Okay. How do you... Adam?
Aiden.
Aiden, sorry. I was off. So it really depends on what you're interested in. If you're interested in brain science stuff, then I might learn about, well, there's lots of stuff to learn about the brain, MRIs and the technologies used to figure out how the brain works. But I can go on and on. If you're interested in vehicles on the ground, in the air, so certainly you should learn about accelerometers, you should learn about gyroscopes, compasses, sensors in general, thermal sensors. I did mention cameras, okay, and there are all different types of cameras. When I use the word camera, we probably all are thinking the visual spectrum, but it could be anywhere within the electromagnetic spectrum. So it might be, if you're working on space telescopes, then you might learn about UV cameras or ultraviolet sensors. Or it might be infrared sensors that you're looking at, depending on what telescope you're working on. Okay, a lot of cool stuff to work on. So sensors, anyone in controls, I would recommend learn as much as you can about sensors. Make that almost a hobby, because that's not addressed much in traditional controls classes. We don't have enough time to do the math, and that's what's in these controls classes. It's mainly mathematical, and again, don't be too pissed off by that, because again, we're trying to deliver reliable, predictable performance, and it's the math that allows us to do that. Now, building hardware is very important too. All right, but if you're more hardware oriented, if you're really hard, you want to really build something, well then you might go into antennas, circuits, communication systems. Now you got to talk to the individual professors because each of these disciplines are very mathematical too. All right, they're very mathematical. Everyone builds something. So we build, with my students, we build ground vehicles, quadcopters. We don't build nuclear reactors, of course. Not yet. We don't have a budget for that. So I hope that gives you an idea. Any other questions? Please.
Yeah, okay, so when you're starting out, when you're starting out controls and some of those like the 480, 481, and you're starting to design for that kind of stuff, what could you go into detail about what that kind of stuff entails?
Good.
Projects?
So the beginning of 480 or 481 is, here's a physical system, like an inverted pendulum. Here's the associated differential equation. And then it's nonlinear. It has a sine theta in it.
Gotcha.
If theta is small, then sine theta looks like theta. And then it becomes a linear differential equation. So we linearize about this. And we study the classic broomstick problem. Now, that may sound boring. I've heard professors say, you guys, that's boring. Yeah, but we wouldn't have gotten to the moon if it wasn't for that. And and understanding this balancing problem, which is an unstable system, also helps understanding epidemics. Because pandemics are unstable systems. So there's a lot to be. So then after you do that, there's the concept, you linearize, then there's a transfer function, which you've seen. And then you analyze the transfer function, poles, zeros, Bode magnitude, Bode phase, and then based on that, use ideas from 480 or 481 to design a control system. And the control system typically takes the form of at least at the simplest level, PID, and that's proportional integral derivative. So you use gains, you use integrators, you use derivatives in order to ensure that that closed loop system is first stable. And then you want to ensure that certain commands are followed, typically like step commands. So that's common to both 480 and 481 at the very beginning. Transfer functions, Laplace transforms becomes your arithmetic. In 481, you move on to discretizing and Z transforms, etc.
Cool.
And yeah, I think it is cool. Although, you know, students, Laplace transforms, that's enough. Z transforms on top of that's a lot. But it is cool, cool stuff. Any other questions? Okay, and then I think with that, we're done. Good luck, and please feel free to come see me or my colleagues anytime. Choose controls.
Thank you.
Thank you.
Sure.